let's get started. Thanks for, yes, we're going to start off with our career panel this morning, and then we'll transition to, showing off your group projects. We're very fortunate to have, in addition to Sarah and I, two people who are actually in industry join us to talk about their experiences. So we have Aristotle Socrates. He's currently at Canberra.
Yeah, Canberra.
And we have Alex Gorbich, also working at NASA. Yes, so I think this is a totally kind of going to be an open.
Sorry, keep going.
Yeah, open free form kind of Q&A session. So like it's totally your time to ask folks whatever questions you have. But maybe I'll kick things off by just asking each of you to like talk about how you got to where you are. What was your kind of career track like, and how you made the transition. So whoever wants to start, feel free to start.
Go for it. I'm happy to go. So yeah, hi, I'm Aristotle. I'm the founder and CEO of Camber. So just for a little information, Camber is, you can go to cambercloud.com. That's our website. So we're a cloud computing company that is basically a platform on top of AWS, GCP, and Azure that allows scientists in any field of science to do their workflows on demand with a single line of Python. So it's very relevant to all of you. So which is part of the reason that I'm here, of course. We just got venture funding a few months ago, and so we've just come out of stealth, and we're going for it. But in terms of my trajectory, so I grew up in the tri-state area, New York City, Connecticut, New Jersey. My parents are from India. I was born in New York. I grew up in Connecticut, and then I went to Columbia and I studied physics, and then I went to Santa Barbara, where I did my PhD in physics, and then I was an astrophysicist for a while. I was a Hubble Fellow at Princeton, and then I was a long-term member at the IAS in Princeton. So I worked in a lot of different areas in astrophysics, relativistic, MHD, black holes, neutron stars, cosmic ray feedback, hot Jupiters, you sort of name it. So, and I was sort of, back then, I was one of the last people who sort of worked on many different areas in astrophysics, and astrophysics I felt became a little bit specialized, and so it made sense for me to sort of move on. And I big data was exploding at the time, and so this was about 10 years ago, and there's this emerging new profession in the tech scene in San Francisco, or the San Francisco Bay Area, called data science. And at the time that I left into the Bay Area, if you left academia and you were a theoretical astrophysicist or a theoretical physicist, you usually get a job as a quant at a hedge fund, right? And I actually had a couple offers as a quant in a couple of hedge funds, but I actually didn't do it, and I moved my whole family. I had 2 kids, and we moved to Mountain View, and there's this program called Insight Data Science at the time, where it's like an accelerator boot camp. I was in the 5th batch, and basically it got you up to speed with the tech scene, and then they make introductions to tech companies, and then they hire you, and that's how it all started off. And I thought I still feel today it's a much better fit for me personally to work in the tech scene in the Bay Area than at a hedge fund in Long Island. So yeah.
Thanks.
Yeah, sure.
Maybe Alex, do you want to go next?
Sure. Can everyone hear me okay?
Yep.
Fantastic. Hi, friends. My name is Alex Gorbich. I am actually a recently graduated grad student. So I just closed 1 year here at NASA back in June. My background, so I did undergrad in physics. Started getting interested in astronomy about my junior year. Then grad school, I was actually there in Sierra at Northwestern. I studied hydrodynamic simulations of cosmological galaxy formation. So, some of the like very pretty pictures of like galaxies, in movies of galaxies merging and stellar feedback and uh, AGN feedback and all that good stuff, like the illustrious simulation, or in particular, I was working with the fire simulations. As part of my grad school journey, I got to, for my broader impacts of my NSF graduate fellowship, I did a lot of public outreach and data visualization. So I was able to merge the two. I built a software application that let me take some of these cosmological simulations and put them into web browsers and like interactively visualize the like tens of millions to billions of particles. And I found that was actually a lot more fun, is telling people about science and writing software to do so. So yeah, I had a very narrow focus when I was applying for postdocs. I knew that I wanted to do something very software heavy, and I wanted to be at an institution that had a mission that was more than just do science. And so when I found an opportunity to work here at NASA so I'm actually in Washington, D.C. I'm based out of Goddard Space Flight Center in Maryland. Um, the scientific visualization studio here, we work with scientists throughout NASA to help them take their science results and create digestible, like Hollywood production quality level data visualizations so that we can make like short form documentary content. Or the project that I've been really involved in is called the Earth Information Center. And the idea is to take climate data into museums. So we're actually opening a museum exhibit at the Smithsonian Museum of Natural History on the Mall September 1st. So that's kind of a yikes for me. That's what my grind looks like at the moment. Um, but these museum exhibits look like these gigantic 20-foot, I think the one at the museum is 31 feet by 11 feet, LED screens, and create like data dashboards and cinematic visualizations that help people understand how Earth data can do things like tell you, if you're a farmer, what the like the water level in the aquifer is like, and whether you need to irrigate your crops. So it was a big pivot for me, coming from galaxy formation to starting to think more about climate data. But it was very fulfilling to think about, like, oh, actually I'm helping communicate this like really important, impactful thing that like might actually make a difference, versus, you know, what I used to tell myself was, important in principle, but was like a real privilege to be able to do astronomy. Is we live in an advanced society when we can afford to pay people to think about what's going on in space. So um, yeah, I think that's in general my career trajectory. I would say what I do now is kind of a mixture between like data engineering and data visualization. I do a lot of like back end stuff to enable some of the visualizers to do things that like they didn't know they could do. So for context, the primary scripting language that we're using here, I know one of the questions is like, what technologies are you using? Is IDL still somehow. So I'm introducing my coworkers who have been with the studio for 25 and 30 years to the concept of Python, and the concept of and the concept of Git, which they're really excited about. Recently, I brought some principal component analysis to this 280 dimensional data set that they were really struggling with, and they were pretty pleased with the results. So it's been an interesting opportunity to bring a lot of the stuff that I was using and learning in grad school to this um, what's the polite way of saying, to this context where, you know, they had a recipe that worked, and why change it? You know, if it's not broken, don't fix it. So we're making things even better. That's what I will say.
Nice. It's great to hear. Thanks, Alex. Sarah, you want to go?
Yeah. So you've all been listening to me talk the whole week, so I'll just talk, I'll keep it kind of short, I think. But yeah, so I majored in physics and math in undergrad, and then I went to grad school for astronomy. And like probably 2 years into my astronomy PhD, I was like really feeling very stressed for like a lot of reasons, but one of the reasons was like I wasn't sure I was like all in on the, you know, academic astronomy thing. I didn't really know about other career paths other than like becoming a professor, and I was like, it seems really stressful. I don't know if I want to be a professor, but I didn't really know what I was going to do instead. And I didn't really feel like I had a backup plan. And people in astronomy, especially nowadays in PhD programs, like it's super common for people to say like, oh, you can just go into industry and go into tech or finance. But I didn't really know what that meant or like how to do that. And so luckily I had a wonderful mentor named Jason Long, who told me that he did an internship in industry before he went to grad school, and it was really helpful for him. I guess I'm giving away your story a little bit.
Fine. It's fine.
Well, he told me it was very helpful for him because he was like, well, I feel like I have this very viable backup plan. I can always go, like, I've done this before, I can go back into industry. And so I was like, all right, I want to do that. So I, during my third year of grad school, so I applied for internships in industry. And I was specifically focusing on software development. I think I would have expanded my search to data science if I had sort of known what the difference was at the time. But I was focusing on software development, and applied pretty much to anywhere I could think of that would hire, that might hire me to do an internship over the summer. And so I got an internship at Google, and I ended up doing that for 12 weeks over the summer between my third and fourth year of grad school. And it was super helpful. Would highly recommend it. At the time when I was applying, I didn't really know anybody that had done an internship like that in grad school, in astronomy specifically. Since then, since I've started like telling people about it, everyone's like, oh, I did that too. And I'm like, well, it would have been great to know you when I was applying. So it's more common than I had at least thought it was. And it's very common outside of astronomy too, like in computer science PhDs, for example, like a lot of people do internships. And yeah, so I think it was really helpful, not only to like, you know, for my original goal of like understanding what the process of going into tech would look like, and giving me an idea of like what the day-to-day would look like. But I also felt like it was really helpful to have a but like have a, you know, a time in my PhD where I wasn't actively working on my PhD projects. And when I came back from the internship, I felt like super focused and like, you know, I understood what I sort of had to do to finish my PhD at that point. So it was really helpful for that as well. Yeah, and now I'm a postdoc. And yeah, I think I am more like feeling better about academic trajectories at this point. I'm still not like 100% sure what I want to do, and I think I will never be. But yeah, I like working with Jason, so that makes it good.
Awesome. Yeah, and I'll just briefly mention, back in undergrad, I was a physics major with a CS minor, and I explored industry jobs. I did a summer internship at Microsoft. In my last year, the year before my senior year, I got a return offer, basically being like at the end of, basically being like, if you sign this, we'll give you a job after you graduate, basically. And I had to decide between taking that 6-figure job offer and applying to grad school, not even getting into grad school, applying to grad school. I'm here now, so I turned that down, but I am now making about the same amount of money as I would have made if I signed that job offer, not adjusted for inflation. So that's, but what you can see is that I know all four of us had quite different career trajectories. We all like exited off into industry and at different parts of our career stage. Some of us came back, some of us didn't, but like we all have kind of, you can see it's very flexible, right? You know, you don't have to commit to one or the other. You can always think about your options and things like that. So that's just one of the things I kind of wanted to make sure everyone understands. So like you don't have to be like, okay, I'm switching industry, like academia is gone forever kind of thing. Okay, so that was just, I just wanted to kind of kick that off so that everyone understands, like you get an introduction to all of us and understand our backgrounds. If anyone has any questions on Zoom, please post them in the chat or raise your hand, and in person, feel free to raise your hand. And the floor is basically open. If no one has questions, I'm just going to read them off the list of pre-made questions that we come up with ahead of time. So anyone have any questions? You want to kick things off? And back.
Sorry. So is it possible to have a position in a university as a developer in astronomy?
So the question was, is it possible to have a position in a university as a developer?
Good question. I think there are more job opportunities that are becoming available for doing software development in academic context. I think they're probably still pretty rare to have like 100% of your time be software development. But I can give you some examples of things that are like that. So at IPAC, for example, which is, what does IPAC even stand for?
Integral Processing Analysis Center.
I'm amazed that you know that. Okay, yeah, so this is it's a little like thing that's run by Caltech. It's right next to the Caltech astronomy department, but it's an independent place to work. And they have folks that do software development as like a big part of their job. So they will like some of the job like requirements are like, or duties, I guess, are like maintaining the exoplanet archive, and like working on visualizations for the exoplanet archive, stuff like that. Some folks there also work on like pipelines and stuff for instruments that IPAC is very involved with. Another one is Space Telescope Science Institute also has some jobs that, in particular, a lot of people there are really involved with JWST right now, and so they do a lot of like JWST, like pipeline development and analysis and stuff like that. Yeah, there are more jobs that are being created like that. I think people are starting to recognize that software is a really critical part of like academic science. But traditionally, it's been hard to get a job that's like purely doing software. Yeah, anybody else want to?
Yeah, I can add to that. That when I was looking for jobs, I discovered the term research software engineer, and it's actually like relatively common in fields outside of astronomy. So it's like, for example, like if like I found a lot of positions supporting like teams of biologists who wanted like an analysis software to do like a thing, but they themselves wanted to focus on like actually doing things in test tubes or running their experiments or whatever. As well as there are a lot of, so I know that the Chan Zuckerberg Institute, which is Zuck's philanthropic organization, runs like an AI meets bioscience thing that had a lot of job openings for these sorts of things, these sorts of positions, both in data science and AI, but also like in data visualization and like kind of like pure DevOps type roles. And so I think that you can do software engineering in like a scientific context. I think if you are more flexible about the topic area. If you want to stay in astronomy, I definitely agree with Sarah. It's happening slowly, I think. I think there's just not a lot of money for it, but people recognize that it needs to exist. Um, I know that the CCA, the Center for Computational Astrophysics, has, I think they're doing 2 software fellowships now, a year. And there was like one other I seem to remember applying for. But there's also like some open source opportunities that like might not feel like you're doing astronomy, but like you're actually having a much bigger impact. So I applied for a role working with Matplotlib. I've seen stuff for SciPy and uh, not it wasn't NumPy, but there was something. I think it might have been like Xarray or something. But you can work on these open source frameworks uh, and still have like be doing a lot of the same work that you would be doing at a university and still have that scientific impact, but really it being a lot broader. So I'd say there's opportunities, but I think you have to be more open-minded than like having an office right next to it, like in between a professor and a grad student, and sitting there and writing code for people who do astrophysics.
There's a question online about whether there is any demand for people in software for careers in instrumentation. I guess I'll chime in a little bit on that. The answer is yes, there is some. You do have to work in kind of the traditional sense. There are software people that need to program the interface between the hardware and the software layers. So it's working at a very low level. You have to understand like hardware, like device drivers, like network communication protocols, memory access, like very bare bones, low level things. But and those are things you can learn. And it's kind of like learned on the job for most people, I would say, of the people that do work in that sector. Nowadays, I think as data pipelines have become more of a requirement for instruments, now there's more people hiring people to do data pipeline development. Haven't seen any of those as like permanent positions, but definitely people are being hired as like research scientists to basically write data pipelines for instruments. Anyone else want to chime in on that?
No extra knowledge on this.
Yeah. There are lots of people getting hired to do instrumentation here at NASA, especially at Goddard, where we do a lot of the assembly. We're actually assembling Nancy Grace Roman Space Telescope right now in the high bay. And there's like 24 different instrumentation projects going on at NASA at any one time. And when I look at the like contractor job boards, it's full of people. They're looking for like electrical engineers and people who like know how to make these things. But I definitely think that having that domain knowledge coming from astronomy would be helpful.
So I just finished my undergraduate degree in physics, and I know in the near future, graduate school is absolutely what I want to do. So I wanted to ask what and I've noticed that academic jobs in the post-baccalaureate sphere are a bit difficult to come by. So I was wondering if you know what that track post-baccalaureate, maybe through post-baccalaureate fellowships or through industry jobs looks like. What do you recommend is maybe the best thing to be doing to get into graduate school in the near future?
Repeat the question.
So the question was, after graduating undergrad, maybe if you're looking for post-baccalaureate jobs, what kind of jobs, either in academia or industry, should you be trying to look for to, if you want to pursue graduate school in astronomy in the future, what should you be targeting for, particular given the fact that post-baccalaureate jobs are pretty hard to find?
I would say that doing research or doing something that's adjacent to research is probably the best way that you can strengthen your applications for grad school. There are a couple of post-bac position, like formal post-bac positions that you can apply for, and I would definitely recommend like applying for as many of those as you can. And then in addition to that, just reaching out to individual people that might be willing to fund you for a post-bac position on grants is also a good idea. I did a post-bac position that was the latter. I just was like funded directly out of a grant. And I think I got really lucky. Like, I don't think that's like super common. But it's also worth trying, at least in addition to applying to the formal post-bac programs.
Just had a question, Aristotle, I think you mentioned you did the Insight Data Science Fellowship. I guess my question is, does the Insight program, does that still run? And do you know of, are there other data science boot camp type programs out there that would be available?
So Insight was very, very successful for a while, and then something happened in the pandemic and it had to close down, unfortunately. But there are things like it, nothing quite as successful or influential as it. I would say there, for these accelerator programs that are not Insight, you have to pay a lot of money to do it. Like one of them is called General Assembly. So I wouldn't. I'm kind of ambivalent towards those. What if you want a job in the tech sector? I think you have to understand, and this is what Insight really provides, is you have to understand the hiring mentality of the tech sector, which is you're an organization. Hopefully the organization is focused on making money, right? Something that sounds gross. I know that sounds gross, but what I mean by that, when the organization or the sub-organization isn't focused on making money, then it's all about politics and things get weird, right? So if in the good situation, that means that how they view you is somebody who comes in and adds value. Right, so they don't really, it's a little bit different than academia, primarily because in academia, when people hire you, they look at your potential. But here they really just look at your skills. And if you don't have the skills to contribute within a couple weeks, you're going to be viewed as being disruptive to those who are contributing. And so when you're on the job market and trying to get into industry, what you have to do is package yourself, make yourself look like you're somebody who is going to add value. And the easiest way to understand how to do that is look at the job postings. And in the job postings, they have basically, this is who we are looking for. These are the skills exactly that you want. And then you have to throw out all the things on your resume, like Fortran, C++, IDL, all these things. They don't care about that, right? They don't care that you studied string theory for 2 years and you're really smart. But so throw all that stuff out and put as much that's relevant in, and then the gaps you have to fill out. That's what you have to fill out. And then when you get the interview, and they go through the multiple rounds of screening you, at this, in your first jobs, there's technical screens. That's what they're looking for. So, can you execute on these skills that they're talking about? The most important thing, though, in terms of getting a job in industry, which is very antithetical to how a lot of people view getting a job in academia, or maybe not, is networking. So network. Be very vivacious on LinkedIn, and just meet people. So if you want to get a job in the Bay Area, move to the Bay Area, network with everybody that you can. Say that you want to grab like a cup of coffee with them and just pick their brains. People love that. And then they'll be like, oh, you know what? Like my friend who works at X company is they're trying to hire into their team, let me make connections. And that's almost how everybody gets a job in at least in the tech sector in Silicon Valley. It's through network, so. I hope that answered your question.
As to add another pro tip is to find an astronomer working in tech and email them. They're more receptive to responding to your emails. Yeah, I think you'd find these startups with like a very large percentage of PhD astronomers working at them.
Yeah. Stitch Fix, there's this company Stitch Fix, which is like about clothes, you know. Have you guys heard of this thing?
Yes.
So, I mean, I was invited to, you know, like apply there because there's a lot of astronomers there, and they have this Friday thing. They have this like ungodly large data science team, and they have this Friday like coffee or like drinks or something where they show off some things that they were doing in the week, and it was like a astrophysics symposium. It was really weird.
My manager at Google was also a physics PhD, so definitely is true.
Questions?
Yeah, so well, I just really quick wanted to add something to the previous question. In terms of fellowships, there is one run out of the, I think the magic of the Insight Fellowship was in the industry partnerships. You know, it's that networking is so important. And so that they were able to actually bring in companies and try and match you one-to-one with them. And like you would do presentations, like that is what made Insight work. And so the Erdos Institute run out of Ohio State is an analogous fellowship. It's free that you can apply to and does have some of those industry partnerships. I will say that a lot of the other like things that advertise themselves as boot camps, I find like I'll be a little more saucy here, straight predatory. So they charge you a lot of money, and you have two options. You can either pay that up front, which is what they would prefer, and then they like try and find you a job, or you can agree to like some kind of percentage of your salary that they will take for the first like 2 to 5 years of your employment, and then they like work harder to network and make connections with their industry partners. Um, what I've heard from the people that have actually gone through those programs is that like the actual boot camping part is not super helpful, that they're not learning very much, but that it's that key last part where, yeah, just to Aristotle's point is like it's all networking. And so that they are already interfacing with the recruiters and bringing them in to like present you as an expert really helps you clear that barrier. So I mean, like if that's what you're paying for, and so I think if you're going to evaluate one of these boot camps, ignore the course curriculum. Like these are things that you like can teach yourself. Like you have already demonstrated that, I think, especially now with the skills that y'all have learned this past week, like having gone through the GitHub and like looked at all the lessons, like you are more than capable of teaching yourself like how to do some of these things. Um, and so the question is just like, how are you going to be able to get past that initial like resume, just, you know, clear, like where they just throw it into the trash because like they don't know who you are. um and to like give like some concrete suggestion for like making like that first step into networking. That was really hard for me. I know, like I was not very comfortable just shooting people emails. I started going to like meetup.com stuff. So in DC, there's a really vibrant data science and data visualization meetup community. And so I was able to go and like they give you a little name tag and you can talk to people. And people were actually really interested that I was like very different than them, that I was coming from a background in astronomy. And so they like everybody wanted to talk to me and like find out like, why the heck are you here? And I even got to do a presentation about like a little bit of my visualization stuff from my thesis that people thought was really cool. And then that like really helped break a lot of ground for me. Um, and so, yeah, I would say like that's kind of like a little bit of an environment that if you're not comfortable starting that networking journey, that's something that you could try out. And then in terms of like emailing people or asking to get a cup of coffee, like one thing you might try Googling is informational interview. That's like the technical term for what you are doing when you're trying to grab a cup of coffee with somebody, is like just learn about what they're doing. And I think if you frame it less as like, hey, I want you, like it feels like less sleazy if you're like, hey, I want you to like help me get a job, is more like, I just want to learn about what you're doing and what skills you use like in your everyday work so that I can like go teach myself that. And like I definitely receive emails that I don't respond to when it's just people that clearly want me to like try and get them a job at NASA. But if somebody wants to like, hey, I'm an interactive web developer, like what's your tech stack? Like I will at least respond to that email. And so it's like trying to frame it less overtly as like, can you find me a job, which then puts like the onus on me to like do all this work to like try and find a job opening that's appropriate to them. Please do not attach your resume in the first email that you send to somebody. Like that is a nightmare. Um, yeah, those are the concrete suggestions I would give if you're trying to start this networking thing. But I totally agree with Aristotle. Is that there's two different worlds that people live in. Like whether you are applying blindly in through an application portal or whether somebody is shepherding your application all the way through because they know who you are. And one does not work. You like will hardly ever get a job if you just go blindly through an application portal, is the reality of the situation.
Good insights, Alex. I think there was a question back here. Yeah.
So my question was actually a follow-up of the resume. So you were talking about your technical skills.
Yeah.
That companies were looking at that.
Yeah.
So I was just recently in the job market in academia, and
Okay.
I sent all sorts of CVs, resumes
Yeah.
out to different groups, different institutions, and one of the things that they always look for was, well, your research projects,
Yeah.
what did you do, and so forth. When it comes to the resumes that a company is going to be looking
Yeah.
at, you highlighted, okay, I have, I don't know, 12 years experience coding in Python, something maybe they are interested in. But when you want to talk about like how you apply your skills, you'll have to then refer to your projects. How do you do that without becoming academic, but more tailored to a company?
Right. That's a very good question. And
Repeat the question for people.
oh, sure. So what is the difference between an academic CV and a corporate resume? And what's really interesting, one of the things at Insight, which I thought was a bit unusual when they told us we were going to do it, which it was, we're going to spend a day and a half doing like a resume seminar where they actually go into great detail of how you should craft your resume. Because it actually matters quite a bit. Because if you look at the mechanics of hiring, in these companies, especially if the company's larger than 30 people, there's either an HR team or a very distinct hiring manager who is funneling and looking through a lot of resumes. And some of those resumes come online, but they have recruiters too, who go out and basically collect these resumes. And so you're looking at a lot of resumes per day. So say you're a recruiter at a company. And so what they're doing is they're looking for a pattern and keywords. And so the keywords are your skills. And those skills have to really match with what they're looking for on the job requisition or the job description that they have online. And then there's a very specific way to go and to describe what you've done at different companies. And it has to be in terms of actions that you did and results that you've had. So if you want, I mean, I could send you a copy of my resume, which looks, I mean, it's literally, it's stale now. Like I'm a CEO, I'm not applying for jobs anymore, but so it's a little stale, but I'm happy to send you a copy of it, and you can see it's just there's nothing genius, there's nothing original about it. It's just very obvious what I'm trying to do for the recruiters and hiring managers who are looking at it.
Send it to us, we can post it in
Sure.
the Discord for everybody to see.
Okay, oh, now I'm nervous.
Yeah. So I can, so I can give an example of one way that I did that, like very explicitly is so, in like an early version of my resume, I talked about how I analyzed cosmological galaxy formation simulations of small patches of the universe, and like it's totally pointless, like did not help. But then reframing that as like, distilled information from relational database with billions of rows and, highly dimensional, like when I was able to like use a lot of those keywords that I didn't know that they were keywords, like, but then once I started to learn, more of the jargon, I was able to reframe some of my skills to be more along those lines. So it's like trying to think more in the abstract. So like rather than refer to your project whatsoever, it's like do like Aristotle says, just talk about things that you did, like what their outcome was in like a very vague sense, but in a very like in terms of like what the impact was on your project vague, but in a very like concrete and like overly technical way. I think if you take that perspective, you will end up finding the right ground where you're like, oh, this is the database that I interacted with. This is how I interacted with it. This is the size of the database. This is, these are the things that people care about when they're trying to hire you, to try and figure out like where you're going to fall.
Another thing I can add to that, which I think is also actually good advice for applying for academic jobs, is that it's good to focus. So a piece of advice that I got was that it's good to focus on the impact that you had rather than what you did. So not like I did this and this was the method that I used, but I produced this result. And, like I was talking about working on a pipeline for an instrument. And like, so I could say things like, improve precision of this thing by 20 times or X% or something. And even if that means nothing to them, they could be like, oh, this person is improving, like they're coming into this project and having an impact.
There's one question on Zoom, so I'm gonna do that one first. How common is it for people in academia to do consultancies for tech companies, say AI or space tech? Are there other industry domains where astronomers can be involved while still working in academia?
Yeah, sure. I mean, it's America, you can make money. So I'm actually on our team, we have 3 faculty, 3 professors of physics and astronomy on our team as advisors, and they're getting equity and in some cases money. I mean, yeah, sure, go for it. A lot of faculty members have, you know what, you see this a lot in biology and in chemistry and in the engineering disciplines. Obviously medicine as well, right? You see people have pretty heavy hitting positions in industry. She's a Nobel laureate at Berkeley for the CRISPR technology, Jane Doudna or
Jennifer Doudna.
Doudna. She's a co-founder of like a multi-billion-dollar tech company. And there's a professor at Caltech, a female professor, won a Nobel Prize. I forgot her name, but she's on the board at Johnson & Johnson. So don't be, if there's some type of relationship, like an advisory relationship, so on and so forth, don't be squeamish about that. It's fun too to do multiple things on once.
Yeah,
for some people.
But I think that's also. Oh, go ahead, Alex.
Sorry, yeah, I was just gonna say, like, if you want to shoot like maybe a little lower than being on the board of like a Fortune 500 company, you can go to Upwork.com and get like some freelance work that I've had some success with, and that's like been nice for my software portfolio.
What I'm trying to say by that is like, if they can do it, there's like no problem, like in terms of legalities or, I mean, there's so much scrutiny on those people that if they can do it, everybody can do it. So.
I was just gonna say, the discovery is the hard part. Like they have to know you because they want to work with you. So networking is again another thing. Or yeah, having one of these sites that lets you connect people together. Yeah. And there's no questions in the room. Yeah.
I was curious, I know in a lot of fields, having a PhD in that field actually hinders you when you go into industry.
Sure.
Do you find that having a PhD in astronomy and then going into industry helps your resume or hinders you?
So the question was, does having a PhD help or hinder you in industry, in astronomy specifically?
I mean, so I've hired like 100 people in my time. There is a problem when I see a resume that has a PhD in like physical sciences, is that people come in not with the correct mindset of, I'm here to contribute to the team. And so they can be a little theoretical and believe that the job is something that it's actually not, like it's a continuation of their work in academia where, oh, I have this job as a data scientist, so I must be doing machine learning and, try to use the most sophisticated algorithms to do X, Y, and Z. So that you can kind of see that in their resumes or, in the first screen or the second screen. So, it's good to have a PhD because they're like, oh, you're smart. Oh, you're good at math. Oh, you're very technical and educated, and you obviously you can grow very quickly. But then there's a negative to it, which is this person might be coming with the wrong mindset.
So I think that's all just building on what you said. I think it's important to highlight the skills that you have and like communicate from the outset. If you're a PhD applying for industry, that like, I am gonna come in and contribute X, Y, and Z specifically. So not being like, I have all these accolades and blah, blah, blah. It's more about skills.
Exactly.
And
Yeah.
Let's go over here first.
You ever feel like, I'm not on a PhD track just yet, but I imagine that you do a hell of a lot of specializing. Imagine that the specialization at the end of your PhD can cause an issue when applying for industry, not being sort of like contributing enough to the thing that you want for your job position, rather that they've specialized for so many years in their field that now,
Yeah.
like that's causing a hindrance to actually jumping into the industry phase.
I mean, to some.
Sorry,
oh,
the question
so-
was that, the question was, does specializing a lot in your PhD help or hinder you in getting into industry?
Sure. I mean, it does. And to some degree that's part of the reason why I started Camber is because the technologies that people are using in the academic world, both in academia, but also in research in industry as well, at places like Boeing and pharmaceutical companies, is really diverged from what's happening in the tech sector. If you want a job in the tech sector. So the tech sector is very cloud-based. And the organizational structure from a technology point of view of creating technology and creating things that consumers or customers use is much different than what you see in academia. There's a huge spectrum of people, from front-end engineers, back-end engineers, server engineers, DevOps engineers, site reliability engineers, data infrastructure engineers, data scientists, data analysts. That's the spectrum of technical people. And the tools that you're using is much different, and how you kind of think of everything and put everything together is much different. So I would, if you want to move into the tech sector, the first thing I would recommend is get on top of doing programs like this that make you good at coding, is get familiar with the cloud and how to stitch things together in the cloud. Because that's really the first thing they threw us in the pool at Insight is we all thought we were selected because we were smart and we're going to do some seminars on statistics and people are going to hire us because we're so wonderful, right? But that's what we thought when we got there. But what they told us is you're going to create a project in 3 weeks You're gonna do it in AWS. It's gonna use big data and machine learning. It's gonna be live in production. It's gonna have a good design and solve a problem for somebody. And you have 3 weeks to do it. And then you're gonna go shop this around. And so it really, that's what basically is happening in the tech sector. So I would say get familiar with AWS and GCP and like understand why there are DevOps engineers. Understand what is a backend engineer, and so.
I feel like we've talked a lot about like how to get into industry, but we haven't talked a lot about what it's like in industry. Do we want to talk about that?
If that's something you want to get off your chest, then feel free. Yeah, let's do it.
Oh, I feel weird now.
Oh, good. You want me to ask you the question?
No.
Oh,
Sarah, what is life like in industry? How is it different than academia day to day?
Thanks, Matt. I don't know, I felt like in the past years, we've always talked a lot about differences, so I was like, oh, that feels like it's missing from this panel, but I don't know, but.
let's go with the flow.
Okay, so go with the flow. But yeah, I felt like life, so during I I don't have a ton of experience in industry. I was there for 3 months. But yeah, it was very interesting. Like the mindset shift was definitely was a lot. And I was even in a research internship at Google. So they were telling me like, oh, we want you to solve an open-ended problem, but it was still like the timeline, the time horizon of like open-ended problems at Google was like 2 months, whereas like the time horizon of open-ended problems in academia is like 10 years, and so they were like, yeah, like, solve this open-ended problem, you have 2 months, like kind of thing. So they were definitely looking for deliverables. They were looking for, they wanted something specific that was implementable by the end of my internship. So that was the mindset shift was very different. And yeah, I mean, like, also like, when I first got there, probably the first half of the internship was just spent like learning the tools that they were using. And I didn't do something like Insight, so I like, had all the skills that basically you all have at this point. And like, I spent a lot of time, Google in particular, like people call it a tech island because they have their own versions of everything. Yes. They have their own version of Google. They have their own version of Python, their own version of Java, their own version, like they do everything themselves. There's an internal version of everything. So you have to like relearn all of these programming languages and stuff. And and that yeah, it was rough. Yeah, so that took a while, and my manager and my manager's manager and my manager's manager's manager were like very involved in like the specifics of like how I was coding, and like I didn't push code to the main branch. I probably did the whole time I was there, but like equivalent of the main branch of Google for like weeks, because they were like, oh, like this particular small thing is wrong, and like they spent a lot of time, like they cared a lot about like the individual lines of code I was writing, which was very interesting, and it was really great to have free food every day.
Your question in the back.
Yeah, I think something that I run into with the difference between academia and sort of industry is in academia, quite a lot of the time, a rigorously proven no is a valid answer. If you go through and you test something, you're like, do galaxies spin at a certain rate because of this? And you can rigorously prove that the third theory is wrong, and rigorously prove that there's a scatter and just nothing will come of this. You can't get any result. That's the result. And in an academic publication, you go, look, you've shown that this isn't viable. And we spent ages carefully doing it. In a lot of industry, you want a product. And if a little way in, you realize this isn't going to work, fail faster, stop doing it, do something else. That we can make money out.
Yeah, it was a good comment about how in industry, in academia, like rigorously proving something as no is a sort of valid contribution. but in industry, it's less exciting and you might want to stop pursuing something if it doesn't look like it's going to give you a deliverable answer.
And you also a definitive no. It often means it's a definitive no that this will not make us money. And there's another aspect to that, is that the reason you were doing that is because there's often someone's idea that it would make money. So you don't want to make it as definitive as possible. But so you have to be careful about that. They don't there's that aspect too, but it's like that in academia as well. Yeah. Right.
I want to ask, in terms of diversity and being inclusive, do you recognize any severe differences between industry and academia?
So the question was, do you recognize any differences in like diversity and representation in industry and academia?
Yeah, I mean, I thought, I mean, if I could be a little, at least when I was in astronomy, I thought astronomy was, a little bit white, compared to the Silicon Valley tech scene, which is, shockingly, there's almost everybody who's a software developer is of Asian or South Asian descent. There are a lot of women at executive levels in the tech sector, and in the venture capital world, it's actually interestingly diverse, where there's a lot of non-white people and a lot of women who have very, very prominent positions up and down the food chain. So, I kind of feel Silicon Valley is, for the most part, pretty diverse, but that's not to say that there still isn't lots of room for prejudice and, cruelty in that dimension. Like Elon Musk is, at the top of the hierarchy there, and you can just look at his tweets and see where he's coming from.
I felt like I had, in my like little subset of the sphere, I had a slightly different experience. I was working on Google search specifically, so like the search team, I didn't see a lot of women, and I remember like in particular like walking in on the first day, like there were a couple, but I definitely felt like not that astronomy is great at this either, but I definitely felt like there were fewer women. But it was one specific area.
It depends on the team. So
Yeah.
DevOps, which are very, very important, developer operations, which are very, very important teams and positions in the tech sector. Very few women, very, very few women. Back-end engineering, very few women, but not as stark as DevOps. But data scientists, there are a lot of women. So, and you see this in academia, like mathematics is there's not a lot of women, very male dominated. But chemistry, there are, relatively speaking, more women. So,
Things like that. I think you see diversity in the leadership roles that usually have a good indicator.
Yeah.
There's more diversity further down.
that's a great point.
Yeah.
I think like the more technical the role is perceived to be, then like the like more white and male it tends to be.
Yeah.
Which is dumb.
That's something. I work as a developer right now. I have 1 year of experience, but I have some kind of problem in my country because I'm from Mexico. That if you study like a PhD, like you are a doctor, you won't be contracted by companies because you are overqualified. So I have a bachelor of geoscience and astronomy. It's like the higher degree that you are permitted to have in order to be contracted by companies. I don't know how is the way in the USA,
No,
It's a problem in my country, so
yeah,
if I end my master's degree, maybe I will have problems finding jobs in the university.
no,
Yeah, there was a really good point slash question about how in Mexico, there's like, if you have a PhD, it can be problematic to get jobs because you're often over 25 by the time you're finishing your PhD. And you're asking about whether that's a similar problem in the US. Yeah, you were saying, I don't think that's much of a problem here.
no.
But yeah, it's also a good reminder that all four of us are speaking from a US perspective.
So we're at the top of the hour. Is there any last questions? Anyone has? One last question.
Sounds like there is a clash in industry between being very particular about the code and also pushing everything out fast. How does that work?
Yeah, it's a good point. So the question is, it sounds like there's a clash between being very particular about the code and pushing everything out faster. I feel like personally, that's not really a clash. It's sort of the same argument that you can make to like, why would you document your code? It's just going to slow you down. But I think in the long run, it does actually save you time because when you're going back to your code and trying to remember what you did, a year ago, the documentation actually helps you. So I think that's a similar sort of perspective, at least, that they were sort of taking. Like the idea was that, okay, we're going to invest a lot of time up front to like make sure this, random intern like understands our syntax and whatever. But then it's gonna, she's gonna write good code at the end of the summer and we'll actually like get something useful. Yeah, but it's definitely a like, we think this will make us more money in the long term kind of thing. It's not like we just want to help her kind of thing.
You guys, one more thing? We can make time.
I was wondering, like, I feel like a lot of the time when you're a PhD student, you're kind of evaluated for your like individual paper or your specific like contribution. But a lot of the time, like maybe in industry, in terms of working on a project with a lot of people together. So I was kind of wondering if like, and obviously your contribution matters, but I was wondering how kind of the day-to-day varies in terms of very much individually working or more in teams or things like that.
Yeah, I'm assuming you're about equidistant from the microphone, so I'm assuming I heard you online and I'm not gonna repeat.
Yeah, I think so.
Yeah, so I think you definitely, my experience was definitely that I was working on a team, but they definitely did still care about my individual contributions and they would count, the metrics are different, like, they don't care about like number of papers or whatever that I publish. But they did care about like, number of lines of code I committed and like, number of pull requests I made and things like that. And those types of things, like there was definitely still this idea of like, you want to keep track of the like body of work that you're producing. And that's the thing that you're going to be evaluated on. And my partner is a software engineer at Google now, and he's been working there for 2 years. And it's very similar in terms of like he just went up for promotion and he had to like put together like, here's all the code I wrote, here's all the, impacts I had on these individual projects. I improved the speed or whatever performance of this by X%. And that was the thing that he was evaluated on for promotion. I understand that I've been given to understand that as you get higher up the food chain too, they care more about like, less about like the, number of lines of code and more about like, have you, at Google specifically, they care about, they call them docs that you write. So if you've like written something about like, here's an idea for how to improve this thing and here's how I implemented it, blah, blah, blah. So it's nothing near like a paper, but it's sort of similar evaluation of writing and ideas and stuff like that. I can probably have more insight on that.
Yeah. Well, there's two tracks that in tech companies. There's what's called so this is an interesting concept. There's the individual contributor track, and then there's the leadership track, right? And they actually, at very large companies like Google, there's a certain number of steps or ladders in the track, and in the leadership track, it goes all the way to the CEO. But both for individual contributors and leaders, there's the same number of tracks, and they get paid in terms of salary, not salary the same amount. So as you go up the individual contributor track, it's not so much about how many lines of code did you commit, or like how many commits did you have, right? it's how many new frameworks have you initiated, you know, for a protocol for passing around types of data, you know, in this networking system for this subset of products that we have, you know. That's how they they measure you. So you go from being in the individual contributor track, from being a developer to more of what's called an architect. So, and then in the leadership track, it's like, okay, how much money? It's really, it all adds up to how much money did you help us make? So, one way or the other. So.
Okay, I think we're out of time, but let's thank our panelists again.
All right, all right, let's get started with presentations.
Muted, please mute, and if you haven't, turn your volume all the way down.
Yeah, turn off your speakers, mute your speakers. Whoever's logged onto Zoom, make sure you mute your speakers. I don't hear myself anymore. I still hear myself. Who's logged into Zoom? I hear someone logged into the Zoom.
Make sure you're muted, and also you're muted on Zoom, and your volume on your computer is all the way down. Is it that?
Oh, no.
I'm sorry.
Okay.
Yay.
All right, let's get started. Everyone has around 4-ish minutes to present and 1 minute in transition between groups. So hopefully it'll work out. Take it away.
And I'm Nazar.
Our project is called Horoscope. So there's a long history of people observing the sky and trying to make sense of what it means in the context of our lived experiences, ranging from Stonehenge in the UK to Chichen Itza for the Mayans to Susan's astronomical clock from 11th century China. And while astrology is our experience with science, it still retains like large cultural relevance today, which is why we think its utility is really in its ability to connect people. Zara and I are both really passionate about both science community and bringing people together. So we view our package as a way to connect with people who have already demonstrated an interest in the movement of celestial bodies. So sort of like, okay, I see you're really interested in like the sun and planets and how they move through space. Have you heard of planets like the one we live on that are outside of our solar system? And using that as a springboard to then talk to them about surveys like TESS that find these exoplanets and any other cool recent astronomical discoveries. And so we created Horoscope, which generates a user's horoscope, life suggestions, lucky numbers, based on orbital properties of their nearest to zenith transiting exoplanet at the time of the completion of their birth.
Right, and we'll transition quickly to overview of the package. So you can pip install Horoscope, _horoscope. Then you very simply from Horoscope main import user. And then you set up the user, you enter your name, the location. If you're in the United States, it's a city and state. If you're outside of the city and country, and then your year of birth, month, day, hour, minute, and second, if you know that precise. You can, if you want, you can check the coordinates of the zenith. You can get the parameters of the planet more directly. But the fun part starts. Get horoscopes. You'll get things like you prefer stability, very adaptive thinking style, stable and enduring. You can get life suggestions. You can focus on little things, lighthearted and flexible approach this week. And of course, lucky numbers, very important. So now we have about 30 seconds. First, we want to thank everyone.
Thank you for making this possible. We had such a great time. Love you all.
It's been really fun. And we'll do a live demo.
Yes.
Live demos always work the first time. All right. Who wants to be the person to know your destiny? Okay, Matt was first. So we're gonna do. You'll have to tell us all your personal information, including
This is recorded.
security note. Sorry, what do you mean? City name and state. Ballston Spa, BALLSTON. BALLSTON. And then space, SPA.
SPA. Well, let's see if that works. What's your year of birth?
Well, it's a town. 1990. September 27th.
All right, perfect. Let's see if it works. It did? Okay.
All right, what's your future?
Oh, no. Your Earth exoplanet is XO5b orbiting star X05, based on a centricity of 0. You're perfectly stable. With an orbit centered major axis of 0.05 AU, you're close to the action and constantly influenced by your star's energy, suggesting a very outgoing and active nature. I can see that. With the birth exoplanet period of 4.19 days, these rapid orbits suggest a fast-paced and reactive thinking style, and with stellar mass of 1.04 solar masses, you're balanced and nurturing.
It's perfect.
Wow. Amazing. Thank you.
If you're ready to invest,
$500.
Make an app. Make an app.
You will.
thank you.
Pending.
Okay, let's see who's next. Group 5. Group 5 in-person group. Yep. Come on down. If you can set right over there, that'd be great. And then share screen. All right, take it away.
Alrighty, folks. So welcome to our presentation. Our project is called Stellar Matchmaker, and we are here to show you what it does. So the first question that you have to ask is why do we want to do this? And hopefully the screen will start flickering because we have a couple of questions. So if you want to match some stars and if you want to sort the images out, it's because you're using differential photometry to mitigate atmospheric effects. So ideally, we have two stars and they got very random noises affecting them, but if you notice they're the same pattern because they're shining through the same atmosphere. So we can subtract that effect, divide them by each other, and we get a lovely, nice light curve, although I made it with a straight line because it didn't probably work out. A demo version of that. But in reality, of course, real data isn't perfectly similar, and not all stars are perfectly the same way it's selected. So you really want good reference stars, ones that are similar to the target, similar in magnitude, similar in position, similar in color. And this allows you to still extract things, because if you don't choose ones that are similar in magnitude and similar in color, then even some fairly subtle effects, I'm pretty sure you couldn't tell that this blue star was getting fainter over time because of reddening in this effect. But when we plot it on our relative chart, we start to see that effect of red is getting brighter relative to the blue. So when we're dealing with inexperienced observers, for which a lot of our projects based for citizen scientists like Exoplanet Watch and ExoClop, they have to select the reference stars, and it might be a difficult thing to know which ones to do. So we have an automated recommender system that will help citizen scientists to choose their references. So demo time. Okay, so we have a script, and that script will run, and we'll ask you the coordinates. Now we're going to put a GUI on the front of this, but there's a set of coordinates, and if we just enter through those, we've got a set of default values, which are for TROPIST-1.
Make the text a little larger.
Maybe.
If not, no worries, but yeah. Don't need to do that.
So it's just entering the position magnitudes of the target, position and magnitudes of the references, and it produces this plot where we've got our target in the middle, and we have all of the potential references arranged, size representing their brightness, the color representing their color in BP minus RP, and the green circles are ones that are close or similar enough to our target that they could be good references. Now, we did have to cheat with this slightly because TRAPPIST-1 is about 4 magnitudes red and therefore way off the chart, and any sensible level of recommendation of color difference would say there are no good ones. So I cheated and said I'd let it be 5 magnitudes color difference away, and just about managed to clip some of the stars because this star is a very, very red one. But that's the idea. You can change those parameters, and we will be changing those parameters to be more sensible, and we'll get this chart out. So that is our demo. Back to the presentation. How does this work? Well, we have functions to get the inputs, read them into an object which stores all of those and can be extensible. We run a query to Gaia based on the inputs. We then do some operations to tell if the stars meet the criteria to generate those colors that you saw, and we plot those using a matplotlib plot. We have our documentation is up. We have this package up on PyPy now. If you really want to, you can just go ahead and go pip install Stellar Matchmaker and then run the script which I just did, Python, run Python. Thank you very much.
Yay.
Right. We gotta keep going. The show must go on. Thank you, though. Group 1 is next. Yes, come on down. You're a next contestant on Code Astro. All right. Let's take it away.
I'm Kristen,
Robert.
Sarah, and we're going to be presenting our package called GalPal. And it's all about making galaxies your palaxies. And so our motivation with this is that, so we all do very different research, so we didn't know like what to do to kind of reconcile that, but we all love teaching. And so we wanted to make a teaching tool that we could implement in classes that we teach. And so GalPal is a galaxy classification GUI, which my friends here will explain all about in a moment. But it looks like this. It's very pretty. And the shining light of all of this is, of course, the meme. So what is Code Astro without memes, right? So I will let Robert take it away.
I'm gonna have to. Okay, so here is GalPal in action. You can see we've got this image in the middle, buttons to classify it as either spiral or elliptical, buttons to switch between galaxies, classify, and then a drop-down menu where we can pick from any of the 10 galaxies that we currently have set up. We would like to add more at some point. And then I'll let Sarah describe what all these buttons do, and I can demonstrate.
Can we put the laptop up here? All right. So here's our first galaxy, and our student who's doing this as part of a class needs to be able to classify whether this is a spiral or elliptical galaxy. So for the class, is this a spiral or elliptical galaxy? Spiral. Yeah. Let's go. So we picked the spiral button. You selected spiral. That's correct. And then we have a little info box pop up with some information about this galaxy and your score. We got 1 right out of 1 attempt. Let's try the next one.
And let's see, I know this is a spiral. What happens if I get it wrong? You selected elliptical. That's incorrect. And now our score is 1 correct out of 2 attempts. We can go to a random galaxy. We can jump around. We can go to our drop-down menu and go to whatever galaxy you want and keep making attempts. Yeah, so we envision this eventually being something we can actually implement for assignments in like our gen ed astronomy classes. That's the goal. It's not quite there yet, but yeah. It's awesome.
Yeah. It's a GUI in 1 week.
Yeah.
Congratulations. Awesome job. All right, next group. Who's up next? Group 3. Also in person. Come on down. Watch the tripwire. Come around. You can come around this way. It's easier. I don't think it's Linda over there.
Guys, since we're running a little behind, I'm gonna start timing everyone. I'm sorry. But when it's been 5 minutes, I'll just say we should go to the next group.
Oh, there we go. Okay, hi everybody. Where's the echo coming from?
You.
Oh, sorry, I thought I needed to turn my mic on.
No.
Y'all can hear me?
Yes.
Okay. Yeah, so our package is called NP Tracer. So the idea here is this is an analysis tool for people who run N-body simulations of planet formation. So I'm imagining most of you probably aren't very familiar with this. So just really quickly, I'll show you what the data from one of these simulations usually looks like. So you get these simulation snapshots. Each of these is like a CSV file where each row corresponds to a particle in the simulation, and it tells you like its position, velocity, mass, and each file corresponds to a different point in time. So the simulation runs, we evolve the motions under gravity, things collide into each other, particles get deleted when they collide, and then they make a bigger particle. So over time, you end up with like less entries in each CSV file. So say you want to do something like make a plot of like the growth of a planet over time. It's not super straightforward to do this. So this package sort of standardizes that process by sort of building some infrastructure where you can just, it spits out a couple of one-dimensional arrays that you can stick on a plot. So that's kind of the basic idea. So I'll pull up our documentation page here. I'll let you talk a little bit about what the different modules are in code.
Okay, so this is like our logo like made by the DAO. Yeah. And then you can see that we have like a few classes. And this like data loader is like the parents class for you will use. And then just like we have some unique parameter for this. And then this is we use for 2 data types, and one is for the simulation. And we have a little function that you can just give in the past for just like both of the data we showed previously, and then you can use the snapshot, and they can continue to read all those like many files. And also, if you're using the Ganga simulation, this is also similar but sort of cheaper because we need to read the time from another file with the function. And then this is the rubber class that is inspired by the overtype, so we can use it to help you to learning like import many things, and we will show this demo later. And then this is our data analyst class that can you input the data that you just read the snapshot from our previous data loader classes, and then give you some parameters, and then we have the 2 functions. The one is that you can get that the stochastic for those particles from each of the snapshots. Then if you want to either like mass or radius or some parameter, and also you can want to choose the function for if you want to the maximum, the minimum, or the median, or the min. And also you can also if you want to trace which particle from those, you can also a function that help you to trace the each given the ID, you can trace how this many particles emerge for some of the form. So that's for the demo. 30 seconds left. Oh, sorry.
Yeah, and we love documentation, but we
develop even more very nice tutorials, so this will make life easier for the people that are going to import these work with this package later. And yeah, basically it's importing like the driver class. For example, we have some simulation data, so the people can make an example. We get the data frame with all the information for all the particles in all the epochs, and just I will jump straight to, for example, some beautiful plots that we can make for example, how the different masses of the simulation have collision and the mass increase or the radius and the new major max. So many.
All right, thank you.
It's 21. Oh, great job.
How can I connect?
You don't have to, you just log on to Zoom and you're okay. And share screen and you're okay.
Everybody who's presenting, make sure you're logging into Zoom beforehand, and mute yourself, mute your computer, and also mute yourself on Zoom. All right, so I'm Zoe.
And I'm Karen.
And this is our project, Chain Plotter. So why Chain Plotter? So cosmologists use two different libraries to do Bayesian inference of parameters via sampling. Both of them being Cobaya, which has its own plotting tool called GetThis, and Cosmosis.
And usually cosmologists aim to produce plots that look like that for the cosmological parameters.
So oftentimes you want to overplot the outputs from both experiments on the same triangle or corner plot, but it's hard to do because Cosmosis doesn't have its own plotting tool, and it's not very easy to make the Cosmosis outputs look like the one that GetThis needs.
So this is where we build Chain Plotter, which takes in a Cosmosis output, the output from the chains from this Cosmosis library, and then makes it readable for the GetThis plotting tool. So it pretty much parses through all the metadata, gets important labels, important arguments, and passes that to the plotting tool, and then we are able to plot. One caveat, right now we've only tested it with like outputs from the dark energy survey data, but hopefully in the future we get more. So I have here a snippet of code for how it works, but maybe I can also I can show you what it looks like. So we import Chain Plotter and this class and this module called GetThis, and then we use the module and we load Cosmosis samples. We load it, and now samples has things like the names of the parameters, the labels, which right now are the same pretty much. You can access the weights, the log likelihoods, etc. And you can package all of that and send it to GetThis, which will make the plot. Unfortunately, the plotting part of these unfortunately, the plotting part takes quite a bit of time because the chains are super long. But you know, in the end, you'll be able to get a plot that looks something like this with the parameters. Or like, I mean, the actual file has like 38 parameters, and like the whole triangle plot will look like that. But yeah, that takes time. So we won't show that part.
So we had ideas for future improvements, such as supporting other samplers, and we only currently support nested sampling, and then support latex formatting of labels, or also any type of Cosmosis outputs, and we only have the dark energy survey year 3 triangle plots.
Right, thank you.
Group 14 is up next. So my name is Zoe.
And Kate.
And Nina. So all three of us work with spectra, mostly to like measure radial velocities of stars to look for other gravitational bodies, including planets. But the kind of the process of just like reading in these spectra and kind of doing all kinds of like data reduction steps can be kind of clunky. And so we wanted to develop kind of a package that would go through some of these steps. Can you show the medium?
Yeah, sure.
So I think initially we were thinking, we'll write a package that kind of does everything you could ever want to do with these spectra. But you know, we ran into some different errors and issues. But I think in the process we learned a lot of these values. And so I think in the future we'll be able to add that functionality and have it be kind of published for everyone else to use. Okay, and then we have Kate will give kind of an overview of all the different things it can do now.
Yeah, so as Zoe said, we originally wanted to make it a package that you could put in data from a variety of telescopes, and then we shortened that down to the telescope that we use, which is HARPS North. So basically the package takes in FITS files and reads information from the header. So if you're not familiar with FITS files, it'll go to a particular column to get like flux and wavelength, and you can plot the spectra, and then there's a lot of processing that needs to be done for that. So we have a function that does a barycentric correction. We also have a function that does the continuum normalization of the spectra and a spline interpolation. So that's essentially just making sure that if you're looking at a variety of FITS files for a day, you make the FITS files, you make the spectra all on the same like wavelength grid and all very similar, so that you can then do various various further processes with that. And then we also have just a function that reads in the spectra and plots the raw data, so you can kind of see what corrections are being applied and how that changes the spectrum.
So we have a little demo. So we do pip install, and I already installed it because it takes a while to install and we're on time on it. And then I did a git clone because we have some spectra examples that are in our repository. So everything installed correctly. I'll import, and I'm going to read the spectra here and then plot the raw data. So that looks right. We're only going to look at 3 orders for now, or else it's going to get a little crazy. This is the continuum normalization. Looks pretty cool. And then finally, we apply our barycentric correction and we do an interpolation. And there's not really any full plots for this, but it spits out numbers, and that looks
Numbers are out. I played correct. All right. Well, thank you. Good job. Right, next up.
Hi everyone, I'm Alia.
I'm Hania.
Kaz. Hey Hanea, have you ever seen that super cool GIF of Planetary System HR 8799 made by Professor Jason Wong?
This is really cool, but direct imaging is really hard and I don't know anything about it. I can't do it, but I would love to make animations of the planetary systems that I like. For example, there's one that has 6 planets moving around the star that I would really, really want to see.
Yeah, if only there was a package that did that.
Yes.
Perfection takes time. So this is our package, ExoViz. Oh.
Any other planetary?
Oh, my bad. Yeah, I would love to see one with a big planet. Got one of those?
Oh, wow. This star is white and it's really bright and hot, then I'm gonna need my sunglasses. Hopefully we could see something cooler and more red. Oh.
LHS.
It's the LHS.
Live demo.
It doesn't work when it's not a real planetary system. Wow. Any favorite systems from the audience? Joey.
How about K23?
We got that too.
Request HD 80606.
There's not enough data in the database. Most of the planetary systems don't have enough data in the database for us to run them, so we're still working on our querying function, but all right. We could try. Yeah. Okay,
Do
so
it.
you said
Try.
HD 80606. Future improvement. I just wanted to work. I'm sorry. We're Trappist. Kepler. Oh.
Ooh.
Oh. Oh yeah, and so we also have the scale on the bottom for anyone who's interested. Actually, like the size of the whole square. And well, if it wasn't clear, the color of the star shows how hot it is. So this is an orange, we saw a red, and we also saw a really hot white.
Awesome.
Awesome.
Good job. All right, group 23. Come on down. Oh, okay, go for it.
All right, so this is our package that we've been working on for the Codastro workshop called Quick Lines, reference to QuickBooks, but not related to taxing or counting or anything. It's designed for astronomers who are interested in extracting quick information about emission line profiles. So let's say you are an astronomer, you have an archival spectroscopic data set of a galaxy, or you have gone to your observing run, you got your data, you reduce it. You just want to quickly know what are the line fluxes, the widths of your emission lines, which has physical meaning in terms of the gas conditions inside galaxies. And so what QuickLines does is essentially you provided any spectra of your choosing. It already has Z Cosmos spectra also hard-coded inside of as well. So you can just give a Z Cosmos ID or use your own 1D spectra, and then it will start to do automatically a Gaussian emission line fitting on a wavelength of your choice. Of course, you can give any wavelength, but there are restraints on the spectral coverage range that you do have. But of course, you will pick like, you know, the oxygen 3 line or one of the polymer series hydrogen lines, and it will give you the emission line profile. So go ahead, Joey, we'll give a demonstration of the code. So here's a Jupyter notebook that I promise is gonna work. So we're gonna show you.
Can you zoom in a little bit?
Yeah. Okay.
It's okay.
Like that?
Yeah.
Okay,
good.
cool. So we already installed quick lines. We imported everything that we needed to like read the data, and then took some sample data that we have in an examples folder somewhere. Here's an example of calling a class within our package, Galaxy. And here are some pretty plots. So the lines that are being shown, this is specifically telling quick lines that we're looking for the H beta line. The one that was on top was the 034959 line, and the one on top of that is the 03507. And actually this symmetry right here, you can see the Gaussian didn't do such a good job, but that also gives you some indication of, well, there's something peculiar happening in terms of the kinematics of what's producing this emission line as well. Anyhow. So it gives you the information regarding the line flux, gives you information regarding what continuum flux density, meaning the emission that's coming right below the emission line, as well as how wide the velocity dispersion of your Gaussian, which also tells you information about kinematics of the gas inside these galaxies. And that's a very quick demonstration, and Jim will talk about the structure of the code. Oh, that's on my computer. Oh, yeah, I gotta quickly share. Uh-oh, cannot share. Why not? I mean, it works. It's also...
Calculations correct.
Okay, yeah. Here it is. Oh.
In fact, we have the idea to create classes, so make the Galaxy class that have the information, the ID of the galaxy, because we have using the C-Cosmos data. But we also permitted the user to use his own spectrum. So if we enter to the Galaxy class, we will see that we have all the documentation, we have all the functions that we used before. For C-Cosmos data, we have the find C-spec function and one to retrieve the 1D spectrum. Also, this is the important one, the fit function, because we use a Gaussian profile. Maybe in the future we could add some other functions to, I don't know, positioning one to fit, to make better fits. We use curve fit to do the fits. Also, we have the return and other handle errors, like here in check input in web coverage, we raise a value error to indicate to the user that the wavelength that the input doesn't exist in the coverage of the wavelength of the spectrum. So we run into problems when writing the classes because we want to use inheritance, but then decided to make an inner class of line here and add the parameters of Galaxy. We need to instance the line class into Galaxy, so we could add informations of about these functions like the continuum flux density, the line flux, the velocity dispersion. That is, it is the most important physical things that returns this program of the fluxes. And then you saw the plots, so it's working.
Right. Okay, thank you. Good job. Next up, I think we have a remote group, group 7. So feel free to unmute and share your screen on Zoom. I think this is Samir.
Yeah,
Oh, are you actually here? Oh, never mind. Sorry. Wrong. Next one, next to the remote group. That's my bad. Oh, wait, which one's the remote group? I forget now.
Oh,
No, you keep going. You're good. You're good. Which one's the remote? Yeah, that's nice. Okay, sorry.
hello all. Today I'll be discussing our work on unveiling Galaxy Halos using PyAlf. PyAlf is the package that we developed during Code Astro. Briefly, the purpose of this project is to understand the halos of galaxies. It is estimated that more than 50% of the baryonic content of the universe is in the halos of galaxies. However, very little is known about the galaxy halos. And one important way by which we can understand these halos is using absorption lines seen in the spectrum of galaxies. But even identifying and classifying these absorption lines is a challenge. This is where PyAlf comes in. PyAlf stands for Pythonic Absorption Line Finder, and the name ALF is inspired from ALF. It was a sitcom in the late 90s, where ALF stands for Alien Life Form. He was trying to make sense of the Earth, and here we are trying to make sense of extraterrestrial data using PyAlf. So this is our group: Isaac, Julissa, Dazi, Saloni, and myself. This is a quick demo of how to install and run PyAlf. So we have a page, a simple description of how to do it. We have a toml file to install. Here I'm copying and pasting the lines. Then we have PyAlf version 0.1.0 installed. Running it is as simple as supplying the quasar sightline as an input. We supply it as an argument. So there's a database. So it queries the database and we put in that quasar name. And what it returns is a bunch of identified absorption line systems. So we have an output folder appended with images, and we have a bunch of images. And for brevity, I will show two of the identified absorption lines. So here we have two identified systems from the bunch of systems that were identified. Now the good part about PyAlf is that it not only identifies strong H1 observers but also weak observers. Some of the existing versions of such line finding algorithms are tuned to identify strong H1 observers, which make use of the fact that there is saturation in the core of the line. But what we have done is it is not only searching for such saturated profiles, but it can also identify profiles with no saturation in their core. So we have a doc string in place with different functions that are doing the line identification. This is work in progress, but we'll be getting there soon. And for future, we have done the profiling and identified some of the most time-consuming steps. As expected, it's a nested loop, and we are trying to either make the code more structured or implement parallel processing. And thank you for organizing this wonderful workshop where we got to learn about open source package development. And thanks to our TA Siddharth who helped us during this.
Awesome, thank you. I think now we have a remote group. So that's group 27. Is that Dennis?
Yeah. Can you hear me well?
Can you try again?
Hello, can you hear me? Sorry. Can you hear me well?
Yes, now it's better.
Okay. So I will start to share my screen. Yep. No. Which one? This. All right. Are you guys seeing my GitHub repository?
Yeah, we're seeing your screen. Your GitHub.
Right, good. So, hi everyone, I'm Dennis. I'm working remotely this year, and the contributors of this work is me and Balaji. And I'm going to talk about this little repo we developed. As you can see, first we have this super professional logo, which is the idea of our repo. And we also love a lot of badges. Badges are super cool. And if you don't like badges, you should do. But anyway, our idea was something that could help us to manage, for example, if you have a repository with a large amount of data, like temporal series, observation, and you don't pretty sure what is happening there, this package could help you to manage all these files and kind of type of observations like calibrations, like flat, like bias, or some sort of objects that people observe there. So it named it with File Manager, or abbreviated as FileM. And you guys can see here for easy how to install the package, how to use it. And if you're interested, you can just do pip install on your machine. This is should get everything working. And to make everything work, we will need a couple of images, like Fritz file image. In this link you can find these files, right? And you should download it, extract these files in your machine. You will see a folder named Fritz with a lot of different files, a lot of different observations. And together with that, there is an example notebook file that with some different cells you can run for this repository. And we hope, at least locally, it worked. It will show you different kinds of files or observations that you have in there. Like an online demonstration, I would like to show you this. Okay, so here is the local repository.
We're just seeing your web browser, so if you're trying to go to a different window, we don't see the other window.
Oh, okay. Let me see. Maybe this. What about now?
Yep.
Okay. So if you start the file, the zip file, you will be able to see all the Fritz files in there that it is used for this example. And here is the Python notebook we prepared for you. We have here 3 simple examples telling us about how the package works. Let me just run the import first. And in the first example, I will just print out all the content of the folder. As you can see, there's a lot of files and files in the subfolder to give us a first overview about what's happening. So you can see the name of the file, the type of observation, like is a bias of 0, it's a flat or a focus series, and also the timestamp where the image was acquired. Okay. Then we have a second example when we can store our data based on a given timestamp. And if you say, hey, okay, yeah, I want to take this image and start during the middle of the night. You can give this timestamp for the code, run it again, and voila, you have those images. Or another functionality we have, you can sort by the type of the observation. We have flat and 0 as an example. So the package we're looking for these files, and we print that out for you, right? We just have these 2 functionalities, but we think to expand it to a little more fancy things like, I don't know, maybe combining images or a little smarter certs in your repo that can help you with this stuff. But I think that I think I need to share another screen again. This is okay. But I'd like to say that I like to go all through this step, you know, that we learned during the workshop, and learning how to creating a CI or file to trigger this in GitHub, how to create the doc strings, how to publish something in Zenodo. I had never done that. And just let me know this for you, we have a problem with the doc. So if you guys try to read something here, it's kind of empty. Try to figure out what's happening here, but don't worry, we'll try to get that fixed. Locally, it's fine, but it always happening. Oh, okay, my machine is working, but when we push everything to the website, it has a problem. So this is it.
Read the docs is the hardest part. So we believe in you. All right. Thanks, Dennis. That was great. Everyone's applauding. We don't have everyone on webcam. Okay, next up. Group 9, come on down.
It's there now.
Hi, everyone. What are calls? Introducing our repository Martian Star Hunter. So at the start of the week, we wanted to build something that looked ahead towards the future of astronomy, and what really piqued our interest was the idea of ground-based astronomy on other bodies in the solar system. There's a little bit in the literature right now about the idea of a telescope on the far side of the moon. However, we are the forward-thinking, ambitious astronomers of the future here. So we thought we would get you a little bit more engaged by looking ahead to Mars. So introducing Martian Star Hunter, which is a little bit of Python code that attempts to model the motion of an object in the night sky as seen from the surface of the red planet.
Right, so when we first started to develop this package, I mean, initially we thought it's just going to be AstroPy on Mars, so how hard can that be? The answer was harder than we thought. So a bunch of key differences between planets Earth and Mars that goes into this process when designing an observatory that can be accessed from Mars. So I think the most obvious one was Mars has a different axial tilt. It also has a different rotation period and also a different orbital period. And while thinking about objects that are beyond the solar system, like other stars, their appearance on the sky isn't going to make that much of a difference between Earth. However, when talking about solar system objects, it becomes quite a bigger change. You might be surprised to hear that there isn't that much data on the motion of Earth on the night sky. So some things are easy to implement, and other things we had to kind of build from the ground up.
Okay, cool. So if you want to use our package, this is the GitHub page. So you can get cloned. We have 2 logos because we're a very indecisive group. So you see here, you're in the now called Code Astro 9. Bigger?
Yeah.
Okay. So you can run the main script and it'll get you into Martian Star Hunter with this little drawing. So then we're gonna put our observatory. So for this project is Mars. We're gonna put the latitude and longitude of our observatory, and I'm just gonna make up some numbers here for now. Then the date, so you can put whatever you want. I'm gonna put the first day of the century, and then a target. So let's do M31, and then it's going to run. It's gonna take 3 more seconds. 1, 2. 2.2, 2.3.
We built this before parallelization and profiling.
And there you go. Okay, and then Anthony's gonna explain the.
Yeah, so this is just an ephemeris plot, which plotted the altitude of an object on the sky, and here we have it for both Earth and Mars, so that you can see what the difference would be.
Okay, so do you guys want to try your own choice of target? Okay, because we've only tested M31. So, okay, so we'll run again, Python main.py, so you don't have a choice, we're gonna be in Mars. So any value for latitude and longitude, just, yeah.
Oh.
So that's 90.
What's the longitude? Doesn't matter, they're all fine.
Okay, so should I put 90? Okay, what date? Okay, so. And then what target? No, you can. Josh. Depends on the query. Just tell me a name and.
Maya, M-I-A.
M-A-I-A, like that. And now we're gonna wait our 3 point something second. Oh, no errors so far.
Ooh.
That's my favorite Astro error.
Yay!
Yeah, so the next steps will be we started in Mars, but we will try to do it in more than just Mars. We will all of the solar system. And we will try to make targets like the motion of the Earth, the moons, Mars, the moon, our moon, our own moon, and maybe even also meteoroids. So this is it.
Awesome. Oh, very cool.
Next up is group 10. Come on down. Watch the tripwire.
Oh, sorry. Sorry, no, it's asking me to.
You can go around.
Yeah, sorry. So just need for some permission. Okay.
Yep. Take it away.
Okay, I need to go.
Go around, please. Thank you.
Right. So, on behalf of my group, I'm gonna be presenting feedback curve, which is a package we did basically for fitting rotation curves and deriving the underlying dark matter profile. So this is quite a common problem one needs to do when, at the end of the day, rotation curves are one of the main pieces of evidence we have of dark matter. So a simple problem is, okay, how do you obtain the underlying dark matter profile given a rotation curve? So to do this, we basically developed a relatively simple class which implements the dynamic nested sampler of density, which is basically a relatively robust parameter inference technique for fitting the rotation curve and deriving the underlying parameters. In this case, we use a relatively simple and widely used model, which is an NFW profile. And here I'm gonna, well, we also have a documentation where you can look at the details, but I'm just gonna walk you a little bit through a simple tutorial here. So also as an example and partly as an end-to-end test, we start by, well, you import this feedback curve, the class objects, and then we generated some mock data. So basically this would be a halo of 5 times 10 to the 10 solar masses and a concentration parameter of 15. I mean, it doesn't matter much, it's just as a reference. And yeah, this is how the rotation curve would look like. So here we instantiate the sampler, and then with this run sampler optionality, the function here, we can obtain the fitting results. It's like when you run a dynasty sampler, I mean, some technical aspects where you can assess convergence at a number of points, also calculate the evidence, the importance way, this is more technical. But then, and then here, the more interesting part is we start getting your inferred parameters. So this would be the log of the halo mass, and this would be the concentration. So you can see it matches very well. So just for reference, yeah, I calculated this. So for 5 10 to the 10, you will have like 10.7. So it matches very well. It seems to agree well with the mock data. And you can also get a corner plot. You see the correlations. And then as another thing, so basically the main feature is the sampling, but you can also, it also has functions which calculate the density profile, the mass profile, the velocity, rotation curve from a given set of parameters, like the halo mass of the concentration. So you can run it just with the data or just with the parameters. And here to test the results, the sampler, it plots this, but it also returns the sampler object from Dynasty. And basically here we extracted the parameters, the best fit parameters, the maximum posterior parameters from the sampler. And then we basically feed them back to the rotation curve. And as we see, it matches very well. So in terms of validation, of course, the idea is that you will apply this to real data, but this is just as an example and kind of to validate the end-to-end test. Then here's the mass profile. And yeah, you can also calculate the density and several other things, but you know, this is the basic thing. I try to keep it quick, so that'll be everything. Thanks.
Awesome.
Thank you.
Thanks.
Group 13. Please mind the tripwire. All right, share your screen and feel free to start. Okay.
Hi, everybody. We're group 13. My name is Fred, and we're working with Dionysus, Guillaume, and Elizabeth, with one remote participant, Kenneth Garcia Cifuentes. He wasn't able to join with us with our presentation today, but he helped us a lot with developing the repository structure and some of the important initialization features for uploading the pipeline. So first, I'll introduce our project, Dark Plotter. It's similar in scope to the last project, as you may notice. But what our goal is to build an instructional tool for teaching students about the different models of galactic potentials and translating those into galactic rotation curves. And it's an interactive tool that allows you to adjust the parameters of these functions so that you can see how changes in, say, the Z or the A parameters of like the Plummer sphere potential or of the Hafei potential will change the corresponding velocity curve of the galaxy. And it's plotted alongside the observational data from the Milky Way galaxy. And it's all in an effort to teach you about the dark matter component. How they compare to these functions. So here, next, I think I can show you our wiki. And then, so here's the functions that we use. So this is how we translate from the gravitational potential function to the velocity curve. So these are the different functions we use. We use the Navarro-Frank-White potential, the Ernst-Quist, Plummer, and Hafei potential. And our observational data is retrieved from an actual source. So this is an image of what our program looks like, and I think we can get into the demonstration, right?
Okay, cool. So for the time being, our code only works if we open up a new Qt file. So let's test. Okay, so we can import the main file that has the plotting function. So this is named dark plotter. And then
import the main function that does the actual plot. So it will be that plot, and then if we run this, we get this cool interactive plot. So the user can actually select and unselect which potentials to be plotted, like let's say click on this, and now then the NFW potential is not shown, and you can do this at the potential. Also, the user is allowed to change this A parameter that Brett showed on the functions like this with using the slider. And then the goal is supposedly to match these potentials with the actual orange observational data. So you can actually play with this around. Also, the way our code was written was like pretty much unbreakable because we kind of already set the limits for the range of the parameter. So we added these boxes here so that the user can actually type a value for this parameter A. So let's say if I type another one here, I get a plot, but if I go beyond the limits, let's say I type a negative value, let's say -10, I get an error. So I have to fix it. And lastly, there is this button save plot that one can click, and then we see that our plot is actually saved on the directory. And then you can play with parameters and then, save new instances of this plot. Is there anything answer I can show?
It's also about the accelerations, zoom as well.
Yeah, you can also, this is supposed to be an interactive plot, so you can also zoom in at a specific part of the plot, then go back. Yeah, that's pretty much it.
Awesome.
Yeah, and of course, I forgot, sorry. We thank the instructors and our TA Suchi for making this possible and teaching us so many things this week. Yeah. That's it.
Awesome. Good job, guys. Okay, group 8. I think this is also a remote group.
Hello, can you hear me?
Yes.
Lovely. I'll just share my screen.
Yes.
Okay, I hope you can see my screen. Hi, everyone. My name is Asin. I'm presenting on behalf of my other teammates, Ali and Himav as well. So a majority of us are from Spain right now. So hello from Madrid, I guess. And we decided to make this package called X-binary classifier because, well, we kind of wanted to play around with machine learning and test out what we can do with it. And we decided to make this package that can classify an X-ray binary source either as a high mass or a low mass. And for that, obviously, we had to train like a model. So we tried to, we started by gathering data and combining different data files and making sure all the columns and everything was the same. And then we moved on to training our model. For that, we decided to use like a very simple model, such as KNN, the K nearest neighbor model. And here, after training, you can see, okay, this is not the best ever score, but it's still good. So we got basically 0.72. And it's like a all right score. And from that point onwards, oops, sorry, I think my computer froze. I hope you can still see my screen. Hi, can you still hear me? Sorry, I think like my computer froze for a second. Okay, I can't really hear you, but I'll continue. basically after that point onwards, we saved our model, and we basically used it to write like this function, which would use our model to classify whichever source we gave, either as a low mass or a high mass. In the end, we made like a demo notebook where you can just import our package and open example source file. And in the end of it, I can just quickly run it to show you. So as you can see, it's just very simple. Here, let's say we're importing it, and we open like this data file that's full of X-ray binary sources. And here you can see when it says target 0, this is our answer actually. It says that it's a low mass binary, and when it's target 1, it's a high mass binary. And for an example, let's say we want to test it on this source SAX, whatever it's called, the first one at the top. And we just take the data from that into a list, and without giving the answer, we just give it to our trained model. And sorry, it's taking a while. And in the end, we run the function xBinary classifier with the values we've taken without the answer. And when we run it, as you can see, it classifies it as low mass, just like it was. So this is what our package does. Yep, that's all.
Awesome, thank you. You're missing the like 60 people clapping for you. Thank you. All right, next scope.
So I'll just very quickly talk through our package that we made called Spectra Sleuth. So this is our repo, but the fun part is so yeah, our README file just basically talks through how you can use this. The idea is that you're just identifying emission lines as like a first pass kind of thing, like just being able to point out the peaks in a spectrum maybe you haven't looked at before, and if we can match it to a atomic wavelength, we try to do that. So there's some user controls on how picky you can be with the peaks, but I'll just get to the point and show you what it looks like. So this is our little tutorial notebook, literally just one cell. So it should run. Okay, and it does run. It's pretty quick. You're just finding peaks. So this is what it looks like when you just find the peaks. And then this is our labeling system. So it splits it into like wavelength ranges that it feels are not horrible. There's nothing in the last one, it's boring. We have a few test spectra. We have like one testing file that you can use. It should work with most SDSS spectra, and if you are willing to format your spectra a little bit for other stuff, it would work for that as well, I think. So yeah, that's the idea. Can we just show? I don't know. So we also have documentation, which we thought hardcore. So you have to have a doc string in a class, or it won't be anything. Yeah, you live and you learn. And also, we'd like to thank everyone that helped organize this, and also our TA Maria, who was super helpful and got this cool photo of us.
Oh, nice.
Yes, all right. Thank you. All right, Joanna, after that one.
All right. Hi, everyone. My name is Savannah Gramsci. I worked on this project called Astro with my partner, Rafi Adnan, who is online today. Our project is to basically make pixel art out of real astronomical data. So you can install it off of PyPy. You can install AstroPixel. We were able to get our Read the Docs to actually be on the Read the Docs website, but Read the Docs broke for whatever reasons. But you can see what it's supposed to look like. All right, so we open this. and you guys in our demo on how to use AstroPixel. So AstroPixel, sorry, I lost your data. If you need dependencies, install those. I've already got them all imported here. So what is AstroPixel? It's making Pixar data, like I just said. So the program will basically query a region of the sky, given a coordinate and radius. And then the user can plot the field as pixel art. So let's run through an example. First, you can choose a coordinate to query. We'll start off with Barnard star, but we also have a random coordinate generator. We'll take a random part of the sky to look at. So let's next initialize a star plotter object and choose a size for the image and then radius for the query part of the sky. All right, we've got our object. Next, let's see where our stars are. Got a nice star field here. There's enough stars for us to take a cool image out of. Now let's try and make some pixel art out of it. Ooh, look at that. Very nice. You can see Barnard's star, nice, big and bright in the center there. But grayscale's kind of boring. So let's make it RGB. Look how pretty that is. This is actually using the real magnitudes from these stars from the default catalog here. So these are the actual colors of the stars. It's just by the RGB. So AstroPixel images aren't just limited to square images. You can change the shape a little bit. And it still uses the right coordinates for the stars. We can also use other catalogs of AstroPixel if you want to use something like maybe your own catalog of stars. But for now, let's just look at SDSS, which is the one we already have implemented. You have to make your star plotter object. I'm initializing some subplots here. And then you can see which columns of the catalog query are being used by the plotter's attributes, and then plot that field in RGB. But you can also change which of the columns are being used for RGB. So for this one, I'm going to change it to RMAG. So let's see what the difference is between these two images. You can see this star is a little bit redder here, a bit more yellow here. It's more green. It's kind of nice to compare and see what those different magnitudes are actually doing with the data. All right, so what if you want to use a catalog that is completely different, not one used by AstroPixel? Well, our current implementation uses Vizier, so anything that is on Vizier, you can query. So for this one, we are going to be using this catalog here. And we are going to be bringing a random coordinate from it. Let's see. Okay, so now we can see which columns are available in this catalog to use. So let's see where our magnitudes are. We've got GMAG, we've got RMAG, we've got in our RMAG here, all these things. So let's set the columns that we're using from this random catalog, and let's also set which columns are the right ascension and declination. All right, and now let's plot the RGB. Ooh, look at that. Very good. This is just a random part of the sky from this random catalog that we were able to get plotted and make a nice photo of. And let's kind of play around with another random coordinate here, and this one's just using the default catalog. Ooh, look at that. Very pretty. And let's look at one of my favorite parts in Sky, the galactic setting. See what this looks like. Ooh, lots of red stars there. All right, this is AstroPixel. Thank you guys.
Fantastic. That's super cool. All right. Well, that was a lot of really cool presentations. Good job, everyone. Yeah, and doing it all within a week. Very impressive. Okay, next up, we're gonna try, that works well in the demo, right? For the most part. Next up, try to get some other group to install and use your package. So we'll break out into pairs of groups. For those remote groups, oh wait, you got instructions for remote groups. Okay, for the in-person groups, find someone nearby and pair up. Spend like the first few minutes telling each other, pointing them to the install instructions for your package, and then spend 10-ish minutes on your own trying to install and use your package, and then come back the last 5 minutes and see how far you've gotten and what issues you've encountered. Okay, so
Take until 50 after.
50 after. Okay. Okay, so we have like 25-ish minutes. So break out into your group, break out into pairs. And then remote groups, follow the breakout rooms. I'm gonna make them. And remote groups, I've opened up the
I tried to recognize everybody that was in our remote group.
Oh, okay, so
But it's really kind of monitor the chat to see if everybody unlocked themselves.
okay.
Yeah, well.
Yeah, but what about the binary? We have enough flow.
When you mentioned the person that
Let me go.
Yeah, but
It's we need one, we'll have one in-person group missing the pair. If anyone else.
It's not like. Yeah, but
I would just wait. Then it would work.
Oh, yeah, well, a year ago.
There are a bunch of people that still haven't joined the group, but nobody's mentioned it.
Yeah.
I'm wondering if they're just like slowly getting there, or I don't know what's going on. I mean. All right, everybody. I hope that was fun and informative, at least fun. So in the last 10 minutes, I just want to give a couple of closing remarks. Also, first, I just wanted to say that I'm so amazed by everything you all have done. It's always blows me away every year how much you all are able to do in a week. And I also want to say, if you didn't present or you felt like your code wasn't working or wasn't as good or anything, it's definitely not true. And it's about what you learn along the way. So don't feel like, I hope you don't feel insecure or anything like that. All of you are doing such an amazing job. Okay, closing remarks. So I just want to remind you about all of the things you learned this week. On day one, we covered development environments, programming paradigms like functional versus object-oriented, etc. We got an overview of Git and Git flow. And then in the afternoon, there were some optional lessons on best practices for NumPy, Pandas, Matplotlib, and AstroPy. On day two, we did a little more about Git flow and then had Jason's Git by hand lesson. And then we learned about debugging with VS Code. In the afternoon, we talked about parallel programming and JAX optionally. Then on day three, we went through releasing code and doc strings and Sphinx. And Matt killed it this year. Saw a lot of doc strings. And then I hope y'all did something fun afterward on day three. Day four yesterday, we talked about software testing and anti-discriminatory practices. And then in the afternoon, we had an optional profiling lesson. So hopefully you are now able to use the language of software development. And just one more reminder about the vocabulary list. We've added a couple new vocab words this week, which has been awesome. Develop and release an open source astronomy package from start to finish, and write code that follows best practices of software development. Just a reminder that nobody's perfect. We're all constantly improving. And the things that we presented to you are all suggestions, not hard and fast rules. And we don't always follow them. The instructors and TAs are not perfect coders. So I feel like we're all constantly learning together as a community. So don't feel like you need to follow everything we taught you to a T. Learning and improving together is great, and that's the goal. Also, Discord and Piazza are going to stay up forever. You might have noticed actually that we've got, I think, 3 or 4 past cohorts of Code Astro still in the Discord. So you should feel free to use that to keep posting and chatting with everybody via one or both of those mediums. And the materials on GitHub will also stay up forever. The answer keys for all the activities are posted. That's in the announcements channel on Discord. And all of the raw recordings are now also posted in the announcements channel on Discord. We're going to edit the videos of the workshop and post them on YouTube too, so it'll be public for everybody to see probably in a couple of weeks whenever we can get around to doing that. And yeah, we would love to chat more about your projects, your science, your software. So feel free to reach out to any of us, any of the TAs. Our emails are in the intro slides. I want to thank everybody who helped make this workshop possible, starting with our incredible instructors and TAs. Let's give everybody a round of applause. It is a dream come true to work with so many incredible people, incredible TAs, incredible co-instructors. You all are really the lifeblood of this workshop, and we couldn't do it without all of you. And thanks to the Heising Simons Foundation for supporting us. Yeah, we like them. And also big thank you to Madeline, William, and Janet. Madeline and William for putting together all the logistics of the workshop, making sure we're fed, getting us coffee and everything every morning, and planning the workshop dinner. And Janet for handling all of the ridiculous financial things that we have to figure out for this workshop. It was a really, really monumental task, and we really couldn't do it without them. And thanks to the staff at the Holiday Inn for keeping us housed. Let's give all of them a round of applause too. And most importantly, thank you, all of the participants. You guys are the reason we're doing this, and I really love, this is my favorite week of the year, and I really appreciate getting to meet so many awesome people and interacting with all of you, and all of the hard work that you put into this workshop. So give yourselves a round of applause. All right, and then last thing I want to say, this is the 5th year of Code Astro, so I had to take a little trip down memory lane and do a little happy 5th birthday Code Astro. So our first cohort in 2020, half of this is like our friends. You can actually see my partner's younger brother here as well. So it's just like, who wants to learn about code? 2021, we had a slightly bigger cohort. More people started to hear about the workshop. 2022 was our first hybrid year, first in-person year, which was really cool, and it was a whole new set of things to figure out how to do it in person. Last year, was our first year at Sierra, and we got to work with Madeline and Janet and William for the first time, and we had the biggest ever cohort of in-person folks. And then this year has been the biggest ever cohort of in-person folks, and we've had a ton of really amazing remote participation as well. It's so cool to see this program grow, and I am so appreciative of everyone that has made this happen and the amazing community that we put together. I'm gonna cry. Okay, so last thing, we would love if you would fill out this feedback form. This is different from the daily feedback form. We've got a couple more specific questions that we can use to analyze overall how effective the program was. So please fill this out. You're welcome to hang out and fill it out now, or anytime, in the next year, you can fill it out. Preferably sooner, but and then also the project database form is here, so we can keep track of the stuff that you've developed for Code Astro. You're also welcome to fill this out, as Jason said, for any project in the future that benefits from Code Astro. Helps us get money if we can prove that we're helping actually develop new projects. Yeah, thanks everyone. All right, that's it for Code Astro 2024. And the TAs are gonna take a picture. So if you're remote TA and you're online, hang out so we can take a picture with you. All right, thanks everyone.